Welcome to a journey where the passionate crescendos of Beethoven's symphonies meet the mysterious world of quantum physics. Today, we'll explore an astonishing connection discovered by scientists: how the musical patterns created by a deaf composer in the 18th century mysteriously mirror the mathematical equations that govern the subatomic realm. This unexpected bridge between classical music and quantum mechanics reveals how genius, whether expressed through art or science, may tap into the same fundamental patterns of our universe. Ludwig van Beethoven, born in Bonn, Germany in 1770, stands as one of history's most influential composers. His works have transcended centuries, continuing to move listeners with their emotional depth and technical brilliance. What makes Beethoven's story even more remarkable is that many of his most celebrated compositions were created after he had lost his hearing. By 1816, Beethoven was profoundly deaf, yet he continued to compose masterpieces like Symphony No. 9 and the beloved Für Elise. These works weren't just popular, they revolutionized music and remain fundamental studies for musicians worldwide. The complexity of Beethoven's compositions, characterized by sudden tempo changes, unexpected pauses, and intricate harmonics, has captivated not just musicians, but now scientists seeking to understand the mathematical structures that give his music such profound emotional impact. To understand the remarkable connection between Beethoven and quantum physics, we must first grasp what makes quantum mechanics so revolutionary. Unlike classical physics, which deals with the predictable motion of objects we can see, quantum physics emerged in the early 20th century to explain the bizarre behavior of atoms and subatomic particles. Pioneered by scientists like Max Planck and Albert Einstein, quantum mechanics upended our understanding of reality. It introduced a world where certainties give way to probabilities, where particles can exist in multiple states simultaneously through superposition, and where the very act of observation changes what's being observed. This field represents one of the most profound shifts in scientific thinking, moving away from the deterministic worldview of classical mechanics to one where nature at its smallest scale operates according to rules that often seem counterintuitive to our everyday experience. In 2007, a remarkable intersection between these seemingly unrelated worlds was discovered. Physicists Drs. Dieter Zeh and Gerard Milburn conducted a pioneering study published in the European Physics Journal, examining mathematical patterns in classical music compositions relative to quantum states. Their research revealed something extraordinary. Beethoven's musical sequences bore striking similarities to Schrödinger's equations, the mathematical formulations that describe wave functions in quantum mechanics. These weren't just superficial resemblances. The researchers found deep structural kinships between how Beethoven arranged notes and how quantum equations describe the probability distributions of particles. This discovery suggested that perhaps these two domains, one artistic, one scientific, one from the 18th century, one from the 20th, might share fundamental mathematical underpinnings that transcend their apparent differences. The principal hypothesis emerging from Zeh and Milburn's research is fascinating in its elegance. Musical notes varying over time can mimic wave functions governed by quantum dynamics. In this framework, each note in a Beethoven composition could represent the potential state of a particle within spacetime matrices. Consider how Beethoven's music often features notes that seem to exist in multiple harmonic relationships simultaneously, resolving in ways that create emotional tension and release. This mirrors how quantum particles exist in superposition states before resolving into definite positions upon measurement. The precision with which Beethoven arranged these musical elements parallels what physicists call coherent states, special quantum states where harmonic oscillation meets probabilistic distributions. As Dr. Milburn noted, the precision observed parallels coherent states often found where harmonic oscillation meets probabilistic distributions. This observation reveals how the structured chaos in Beethoven's compositions reflects, in artistic form, the same mathematical principles that govern quantum behavior. What makes Beethoven's compositions particularly suitable for this quantum comparison is their remarkable balance between structure and unpredictability. Musicians have long noted how Beethoven's works contain moments of apparent chaos that ultimately resolve into perfect order. His Fifth Symphony famously begins with the stark four-note motif, often described as fate knocking at the door, before developing through complex variations that nonetheless maintain mathematical coherence. This interplay between deterministic structure and apparent randomness mirrors quantum systems, where particles follow strict mathematical laws yet exhibit probabilistic behavior. Researchers analyzing Beethoven's scores have identified patterns in how he distributes notes across octaves, creates rhythmic variations, and develops harmonic progressions that, when mapped mathematically, create distributions remarkably similar to quantum probability functions. This suggests that Beethoven, perhaps intuitively, tapped into mathematical patterns that scientists would only formally discover more than a century later. Beethoven's deafness adds another layer of intrigue to this quantum connection. As his hearing deteriorated, he famously resorted to feeling the vibrations of his piano by placing a rod between his teeth and the instrument. This physical connection to sound vibrations might have given him a unique perspective on music, one based on pure waveforms rather than conventional hearing. In quantum mechanics, particles are described as probability waves until they're observed. Similarly, Beethoven may have experienced music as pure vibrational patterns free from the filtering of normal hearing. This direct experience of musical vibrations parallels how physicists describe quantum systems through wave equations. Some researchers speculate that Beethoven's adaptation to deafness may have heightened his ability to compose based on mathematical relationships between notes rather than how they sounded conventionally, inadvertently bringing him closer to the quantum mathematical framework that Schrödinger would formalize over a century later. The parallels between Beethoven's music and quantum equations go beyond superficial resemblance. When researchers applied Fourier analysis, a mathematical technique that breaks down complex waveforms into simpler components, to Beethoven's compositions, they found distribution patterns statistically similar to those found in quantum systems. For instance, the frequency distributions in the third movement of Beethoven's Moonlight Sonata, when mapped mathematically, create patterns remarkably similar to electron probability distributions in hydrogen atoms. These similarities extend to how both systems handle entropy and information density. In quantum systems, information is distributed according to specific mathematical constraints that maximize both order and complexity. Beethoven's most celebrated works show similar information distribution patterns, with themes developing in ways that maintain both coherence and surprise. These mathematical correspondences suggest that both Beethoven's compositional intuition and quantum physics may be tapping into fundamental mathematical patterns that underlie complex systems throughout nature. The connection between Beethoven's music and quantum physics represents more than an interesting coincidence. It exemplifies how art and science can intersect in profound and unexpected ways. This interdisciplinary convergence enhances our appreciation of Beethoven's genius while opening new avenues for exploring the universe's interconnectedness. For musicians, understanding the quantum-like structures in Beethoven's work offers new perspectives on interpretation and composition. For physicists, these parallels provide novel ways to conceptualize and communicate complex quantum concepts. Educational institutions have begun developing curricula that use this connection to teach both music theory and quantum principles simultaneously, finding that students grasp difficult concepts in both fields more readily when they're presented as complementary rather than separate domains. This bridge between disciplines reminds us that human knowledge isn't compartmentalized by nature. The same patterns and principles can emerge across seemingly unrelated fields, revealing deeper unities in how we understand and express the world around us. The Beethoven quantum connection has sparked innovative research at the frontiers of technology. AI researchers developing creative algorithms have begun incorporating quantum-inspired mathematical structures based on Beethoven's compositions. These AI systems can generate music with both emotional resonance and mathematical coherence that traditional algorithms struggle to achieve. Meanwhile, quantum computing researchers are exploring how musical structures might inform new approaches to quantum algorithms. The way Beethoven organized musical information across different scales, from individual notes to phrases to movements, offers potential insights for quantum information processing, where managing information across different quantum states presents similar challenges. Some quantum computing labs have even experimented with translating Beethoven's compositional techniques into quantum programming frameworks, finding that these musically inspired approaches sometimes solve complex problems more efficiently than conventional methods. This cross-pollination between classical music, artificial intelligence, and quantum computing represents a fascinating frontier where art from the past may help shape technologies of the future. Perhaps the most profound implication of the Beethoven quantum connection is what it suggests about pattern recognition as a fundamental aspect of human genius. Both Beethoven and quantum physicists excelled at identifying and manipulating complex patterns, one through musical notation, the others through mathematical equations. This suggests that genius across different domains may share a common cognitive foundation, the ability to perceive and work with patterns that others miss. Neuroscience research supports this view, showing that both musical composition and mathematical reasoning activate similar brain regions associated with pattern recognition and manipulation. The fact that Beethoven intuitively created structures that align with quantum mathematics raises fascinating questions about human cognition. Are there universal patterns that the human mind is naturally attuned to recognize, regardless of whether they're expressed through art or science? The Beethoven quantum connection suggests that what we call genius might sometimes be an exceptional ability to perceive and express these universal patterns, whether through musical notes or mathematical symbols. The remarkable parallels between Beethoven's compositions and quantum mathematics reveal a profound truth. The boundaries we place between disciplines are often artificial constructs. When Beethoven arranged notes on a staff, deaf to their sound but attuned to their mathematical relationships, he was unknowingly exploring the same patterns that quantum physicists would later formalize in equations. This convergence reminds us that whether through art or science, human minds seek to understand and express the underlying patterns of our universe. Perhaps genius in any field represents moments when humans glimpse these universal structures and translate them into forms others can appreciate. As we continue exploring the intersection of music and physics, art and science, we may discover that the most beautiful symphonies and the most elegant equations are different expressions of the same fundamental truths. A harmony that extends from the concert hall to the cosmos, connecting the passionate creations of an 18th century composer to the mysterious dance of subatomic particles. In this unexpected connection between Beethoven and quantum physics, we find not just an interesting coincidence, but a window into how the human mind, at its most brilliant, perceives the hidden rhythms that orchestrate our universe. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.